Hello everyone, and welcome to another seminar in computer engineering. Today, you don't know it, but I'm in my office. I always try to use some Unicamp background, but I will be honest with you. I'm in my office today and not somewhere else. We are spinning up our 5G network of the Smartness Research Group, and it's been exciting times, like the topic that we have today on edge-based IoT and these orchestration platforms, these lightweight virtualization environments, Kubernetes, Docker, and all this evolving landscape. This is what Simone Ferlin, good to see you. Again, after SIGCOM, we were together in Coimbra having nice time and delivering a beautiful set of workshops thanks to your work, among other contents that we put together in SIGCOM. Again, another plug. If you didn't see the proceedings or the recordings, have a look over it. But now let's focus on today's seminar. Simone, I don't read out the abstracts. It's everything written here. Biographies are of the speakers are always so rich that and our time is so valuable that I skip it. People can read them, find you over YouTube, contact you as well as needed. What I'm looking forward is for your presentation. You can start sharing your screen, and for our chat in around 40 minutes from now. We have good 50 minutes for some chat. I may bring some questions from the audience, from our students. Hopefully they have done their homework and they have shared some good challenging questions for you, Simone. Thank you.
Cool. Thanks very much, Christian. It's a pleasure to be here and to have been invited to the seminar. We talked about it a long time ago, but time and time zones and agendas never synced that well. So I see here that we are about 15 people, and I'm assuming that most of you know a little bit about the topic that I'm going to present. If not, you are free to interrupt me anytime or just put a question in the chat, and then I try to address the question as I move through the slides, okay? So the work I'm going to present here, as you saw in my bio, I have a double affiliation. I'm most of the time working for industry at Red Hat in the performance engineering team, but I also have an adjunct position at the University of Karlstad in Sweden, where I take a little bit more time to do research that industry doesn't have time to do. So they write software, they ship things, and sometimes there are a few questions for people that have this tickling to do research like myself, and I do this work as part of my role at the university. So this is a paper that was presented last year in the ACM IEEE Symposium on Edge Computing. The idea that we had back then was Red Hat was releasing one of its cloud platforms. So maybe you know Kubernetes. So Kubernetes is very famous. Vanilla Kubernetes is available open source for anybody deploying applications that need some sort of management and orchestration. So Red Hat has a product based on Kubernetes that's called OpenShift. This is like enterprise-grade Kubernetes with lots of features and other hardenings when it comes to security that companies can buy from Red Hat and get the subscription, the service subscription, the way that the model that Red Hat operates. And last year we had this technical preview. This is a stage before generally available, which is when we have something matured and released as a product for edge clouds. So everybody knows that we have this idea of pushing infrastructure to the edge of the network now. Instead of reaching out to data centers that are maybe far away from your location and having traffic going through several networks, we are pushing pieces of these data centers closer to the edge. So you could think that very close to the base station where your 5G network is, there is something processing your application there. And then Red Hat released one product in this line, and we decided to have a look at its performance compared to other options that existed in the market. I anticipated already a little bit from the slide here. So edge computing is a term very broad, and sometimes people ask, which type of edge are you talking about? Because there are several layers of edge when you think about edge computing. But the main idea is basically distributing the infrastructure of the data center closer to where the users are, enable, let's say, lower latency because the content is closer to the user. So the travel time for your packets to reach the other side of the application is shorter. And of course, you can optimize bandwidth because you don't have traffic flowing through several levels of the network before you get a response. And many applications in IoT, from smart meters, from Industry 4.0 or smart health, have been trying to leverage this new infrastructure. When I talk about Kubernetes or a platform as such that deploy and orchestrate applications, we usually had, we came into this new road with a different mindset how we write applications. We have this monolithic architecture on the left side, usually is, if I think about some businesses, you would even deliver software and hardware and everything working in a single piece, or sometimes even in a single machine to the customer. And on the right side, in this microservice architecture, which is the mindset of application developers that would write applications for something like a Kubernetes platform, it's way more distributed. So the logic of the application is also broken into several packages or several pieces, better said. How you break this logic? If you write your, let's say, authentication application as 10 microservices or 20 or 300, there is no hard-coded definition for that. So sometimes you would break the logic in smaller pieces and make it very modular and very small, but then we've paying a certain price, for example, in communication, because these modules have to talk to each other. So this is a little bit the difference, moving from this way, monolithic way of writing applications to this other mindset or this other architecture that is a microservice. When you think about containerization and orchestration, so if you look back here on the right side in the microservice, you would break your application in several pieces, right? And we didn't come from this monolithic architecture direct into the microservice Kubernetes way of writing and deploying applications. There was a step in between, or a few phases in between, which were virtual machines. So back in the days, we had hardware that got stronger. We learned how to virtualize hardware resources, to use this hardware for different purposes, not only one application, but different applications. So you would use a full virtual machine for your application and then a second virtual machine for a second application. That was a little bit how people that were used to write monolithic applications came to virtualize or came to break the application sometimes, or not even break, but use the hardware for several applications. But then the containerized or the container logic way of writing these applications is one step further, where, as you see here on the left side, you're saving a lot of resources. A virtual machine is basically a full-fledged operating system with several other layers of virtualization that maybe your applications are not even using. So maybe all these resources are idle most of the time or underutilized. In a containerized way of writing your application, you would have a single layer of an operating system, the physical infrastructure underneath, and then the container engine or the container runtime that would make sure that your applications and basically the libraries that they need run over this single layer. So this is basically, I'm seeing a question here, just a second. I'm going to reply to you. So this was basically the path that we followed from this monolithic through virtual machines and then to containers. And not all industries did this transformation at the same time. So the IT industry followed this path very early. They are 10, 15 years into this transformation on how to write and deploy software. Other industries, for example, telecom, they are a little bit younger in this journey. So they are very much used into writing, in delivering things as a monolithic architecture, but they learned that there are several benefits, or there could be several gains in transforming this way of delivering their products as basically a containerized and cloud-based application. You find that in other topics, in other areas. I can discuss also about that if somebody's interested, but this is just an example how things moved to run on these platforms like Kubernetes. And Kubernetes is basically this system that you can drop your applications as containers. And before you even drop your application, you have several functions, we call it control plane in Kubernetes, that need to bookkeep stuff, need to monitor, need to find some consensus and keep state of things, or make sure that the state that you're asking for is maintained. So these boxes here on the right side are a few of these functions that run on your cluster before your applications are even deployed. So few examples here. For example, etcd. etcd is one of the heaviest elements in Kubernetes. It runs the Raft protocol. So Raft is basically a consensus protocol, which needs to find consensus about state. For example, if you have several copies or instances of your application running and something is changed, for example, somebody deployed something in one of these instances or wants to deploy. So etcd is in charge of making sure that all, let's say, all instances, as long as not pre-defined by the user, have the same state. So you could even define that you want some versions of your application on one part of your cluster and different versions in another part. But etcd is known to be a heavy piece in Kubernetes, and sometimes at the edge, there are some papers discussing if we really need etcd or we could have a different, basically a different protocol with a lower level or a mild level of consensus here. Kube scheduler. When a user interacts with the Kube API and tries to deploy the application, so the Kube scheduler is in charge of finding the right place. We call it nodes, or usually worker nodes, where actually your applications are running. It's in charge of finding which of the worker nodes have enough resources to run your application. There are several works here that are lots of research that could be done here. For example, if we look at resources, is it CPU and memory enough? Should we look at on the communication pattern of the application that we want to deploy and maybe schedule the application in a different way based on the communication and not only CPU or memory? If you have even lower level requirements like hardware alignment, for example, NUMA alignment, is it also something that the scheduler should take into account? For example, making sure that you are not crossing NUMA borders when you are deploying your application on certain worker nodes. So there's lots of research that could be done here, which type of metrics the scheduler could take into account when deploying the application. The vanilla Kubernetes have very basic logic when it comes to the scheduler and several other pieces in the control plane here. But if you go into enterprises that run very large scale internal clusters, for example, Google have their own system. It's not called Kubernetes, although they open sourced Kubernetes many years ago. They probably have something different here because these functions are very, very basic. So other things here, for example, the worker nodes at the bottom of the, on the right side. Kubelet. Kubelet is also an element that talks most of the time with the control plane, the master nodes, as we say, basically telling that it's alive, it's well, and some other notification data also flows to the control plane. And then you have the container runtime on each worker node to run your application, the kube proxy. So depending on the communication, if you have communication between worker nodes, or maybe from a user outside the cluster into the cluster, what we call north-south communication. There are different, there's basically different things that happen in the control plane. And all of this traffic and all of these functions here, they run on your cluster before any application is running. So we had this idea of looking at IoT applications because they were the most interested in using edge computing. There are others, but there are many of these IoT applications that want to leverage the edge as a computing infrastructure. We wanted to check the resource overhead and performance when the cluster is basically idle, when you have no applications running, just the cluster deployed. We want to check the control plane performance. For example, once you start deploying your application or creating load, as we say, how does different functions in the control plane consume in terms of CPU and memory, and also data plane performance when applications are actually sending data, which is basically the most important part for us, for developers and the users as well. As I said, we have different options when we choose this edge cloud platforms. So if I start from the top left side, we have the Key0s, which is provided by Mirantis. have very low system requirements. When I talk about low system requirements, is usually in terms of CPU and memory to deploy the cluster. We have key tray S on the right side at the top. This is provided by Rancher, which was acquired by SUSE some time ago. We have MicroKS at the bottom right, which is developed by Canonical. Canonical is the mother company, basically the parent company from Ubuntu. And then on the left bottom side, the Microshift, which is the technical preview, nowadays generally available Microshift from Red Hat. So we took these 4 platforms, we deployed them, or we checked first which are the characteristics from them in terms of supported OS, or which is the container network interface that plays a very big role in the data plane performance, which are the requirements in terms of CPU and memory. Some of them ask for disk requirements as well. And also storage interface, which is not something that we evaluated in the paper. We focused more on the control plane elements and the data plane. So here you can see that the CNI, so this is the container network interface, varies across these distributions. So Microshift runs with OVNK. MicroKS, Kubernetes, or KeyTray-S or Key0S have Calico as options. Flannel was famous or popular back in the days, but it's not really deployed today in practice. And here we have a few options, but let's say the default, for example, the default in Microshift is OVNK, but the default in the other distributions here are usually the first one, for example, the Calico and the Cube router. So Flannel, we didn't evaluate because we knew that it was deployment-wise or adoption in the industry a little bit irrelevant. And one thing that strikes our attention here is the difference in terms of the requirements. If we're talking about edge cloud platforms, and they promise to be lightweight, well, we have Microshift from Red Hat asking for like 2 gigabit memory and 2 cores of a CPU just to deploy the cluster, whereas the other ones ask for a little bit less. These are the mean specs that we got from the website. And for example, for KeyTray-S, you cannot deploy one cluster with 412 megabyte RAM. You need more. So they put this absolute minimum requirement in the website, but we also found while we did the work that it was actually not true. We needed a little bit more. So these differences here, even in the container runtime, for example, we use Cryo and Microshift at Red Hat, but the other ones are mostly using containerized. All these tiny differences here, how they run containers internally, which CNI they are using for the data plane, they play a major role in the performance evaluation. And of course, if you're talking about footprint, which are the minimum requirements to just put up the cluster. So some metrics that we selected here. CPU, memory, disk, and network metrics. So network, we looked at throughput and latency. And for the control and data plane operations, latency and throughput. And we don't look at things at random in Kubernetes. So we looked at, when we started stressing the control plane, we focused on some objects in Kubernetes. For example, namespaces. if you're familiar with some low-level ways that Linux tries to isolate processes, namespace is a keyword here. How many pods and deployments we trigger. PV and PVCs, this is PV is persistent volume, this is storage, and persistent volume claims for PVC. This is basically when your container requests a piece of storage to save some data. These are also operations that happen in the cluster when you're basically trying to save data to some storage, and also services that you deploy. So on the right side, this is just a little bit visually what is a service compared to a deployment. For example, a deployment, you could include several things like replicas of your application and also define the behavior of the application, and then the storage as operations that these applications can request. So you have to point them to some storage. This is the environment that we had at the time to do the measurements. So we use a microstack cluster. This is basically based on OpenStack. We deployed Kubernetes cluster. This is here in this, around this blue line. So we had a control plane node, and then we had up to 3 worker nodes. And then we had a simulation node with the traffic outside the cluster. You can ask why you are running Microstack and why you are running here on Ubuntu instead of running, for example, in our case, Microshift on a Red Hat operating system. So these were basically some limitations that we had on the setup back then. We had some test bed limitations in terms of resources and also what we could use to do the installation. I think the important thing to mention in these cases is that you measured all the platforms under the same conditions and with the same system. But this is also a valid question why we're using a different operating system here, because you could say that, okay, the edge cloud platform can perform from Canonical is built on top of Ubuntu, so it could benefit more from that. But this is not the case. But this is also something that I wanted to bring up front because we got some questions about it. So the Kubernetes version was also slightly different in some of the platforms that we chose. So this is also something for you to consider when selecting some of these platforms, which version. As I said, container runtime and then the container network interface. So some first results here. This is the resource usage when the cluster is idle. So if we focus on the figures in the middle and to the right. So the control plane shows quite a different behavior for memory, for example, when it comes to Microshift and when it comes to micro Kubernetes. Memory, CPU, and disk usage. So here you see a little bit more visually the main difference of these platforms when they are not running any application, any workload. On the very right, on the right side, here are on the worker nodes. And you can ask, where is Microshift? So Microshift has a little bit of a different architecture compared to the other platforms. Control plane and data plane are running on the same node. So we cannot split exactly the control plane or the control plane node and the worker node, the resource usage, like we can do in the other cases. This is an architecture architecture decision and also main difference to the other platforms. In some cases, this is desired. In other cases, it's absolutely not. You don't want control plane running on the same machines as the worker nodes where your workloads are running. And on the very left side, this is basically the resource usage with the operating system. This is not with the platform, it's just the operating system, the machine that we're basically this setup here where we installed the clusters. So you see a little bit the difference as well from RHEL compared to Ubuntu. So some other observations here from the control plane nodes on the left compared to the worker nodes to the right. The workload that we deployed here is 60 pods, and we looked at CPU and memory utilization. So we deployed 60 pods into the cluster, and then we look at different metrics. For example, we have etcd, the Cube API server, we have the let's look at for example, for the control plane, let's look at the etcd, which I said is the heaviest element, and then the API server. So for the CPU usage, you see here there is a little bit more, let's say, relevance for the key 0s for the API server. In the key tray S, a little bit to the right, you see also some more impact from the key tray S server. And here to the right, for example, from the Microshift column, we could a little bit ignore here because, as I said, it's hard to split the control plane from the data plane, from the worker nodes if they are running on the same node. And then here the micro Kubernetes. So this on the top is the CPU usage, and at the bottom we have the memory usage. So you see that things vary quite a lot between these platforms, even though we are deploying the same application or the same workload, as we say. When you look at the worker nodes, where the applications are actually running, where the 60 pods are actually deployed and running, we also see quite a difference here when it comes to CPU usage and also memory usage. For example, if you look at the key tray S and the micro Kubernetes and the container runtime, or even the CNI, you see, this is just to quantify visually that we actually see some difference. It's very hard. This is also something we got criticized in the paper. We didn't say where this difference come from. This was not the goal in the paper. The goal in the paper was basically look at these edge cloud platforms as a black box. We deploy the application and then we look at how much in terms of the resources are being consumed. But you can see here that even though they might be using the same container runtime or the same container network interface, the same CNI, you still see some differences in their performance. So if we look here at 3 pods per deployment, remember the deployment is basically you can group a few containers or pods in the same deployment file and define some characteristics. So we did here 3 deployments. And then we varied the number of deployments. We went from 1 up to 64. And then we looked at the average latency and the average throughput. This is here, the average latency is when these pods are up and running. This is what we call the pod ready state. And we measure very often something that's called the pod ready latency. This is a metric that we defined internally a little bit at Red Hat, but this is basically the point where you try to deploy your application to the point where this application is ready, available, and running. And here again, you see quite a difference as we grow in number of deployments. This is basically, you could imagine that there are several users, or basically one user sending several deployments at the same time via the API server to the scheduler, and then the scheduler have to figure out where do I place these pods. So you see quite a difference here as this number grows in terms of latency for the pods, for the micro Kubernetes and Microshift here in this case. For 64, I think we didn't have the values for Microshift because we exceeded the resources that we had. Remember that control plane and worker nodes, they run on the same machine. So we didn't reach to the point to deploy 64. So for Microshift, the limit in terms of resources was reached between 32 and 64. That's why we don't have results for it here. And the average throughput, this is pods per minute. So in terms of how many pods are actually scheduled over time. So we see here also quite a big difference as we increase the number of deployments. Remember, the number of pods per deployment is fixed, but we increase the number of deployments to see how things scale. Here we changed things a little bit. We have 40 deployments with 120 pods, and 40 here because this is the last value we got. I think if I remember correct in the paper, I think this is the last value that we got measurements for the Microshift, because after that we reached the limit, if I'm not wrong in the paper. But here we have this 40 deployments with 120 pods, and then we set different actions. So it's basically create, list deployments, there is an update, scale, or delete. So delete a deployment. And we also see here that in terms of latency, things vary quite a bit. So the micro Kubernetes here, especially in the part that delete is a complicated, operation, but especially the part here for scale and creating, there are a few spikes here that look very suspicious in one particular case, the micro Kubernetes. And here also to measure the scalability of the API. Remember, the API server is the interface between the user and to the inside of the cluster. We also deploy 40 objects, and then the different objects is basically namespaces, services, persistent volume, and persistent volume claims. And we also see some strange spikes here in two different distributions for two different types of objects. And in one particular case here, micro Kubernetes has also a little bit, or I would say quite a higher latency compared to the other platforms. So I think this is my last, or one of the last slides about the data plane. As I said, the data plane is about latency and throughput most of the time. In a cluster, we have different ways of communication, or how the communication is implemented. So we have usually communication that is east-west, as we say. So this is one worker node talking to another worker node. So usually this communication goes down to layer 3, layer 2. Layer 2 in the cluster in Kubernetes is implemented with OVS, and then they reach each other over this interface. And then we have communication that is north-south. So north-south, what we say is usually someone outside of the cluster talking to an application inside the cluster. You can imagine that CDNs nowadays are actually like this. So you are the user trying to reach some content from a CDN, and the CDN is probably running something like a Kubernetes or such a platform to orchestrate content to the points of presence. And your communication with this point of presence would be more or less this north-south. And then we have different ways of enabling this communication. Cluster IP and node port. These are basically different ways of having IP addresses. So some of them, if I remember correctly, uses the actual physical or the actual IP address of the physical machine that is hosting the cluster. Others have some other mapping of IP addresses. You don't use the actual IP address, but there is some level of logical IP addresses. I don't remember exactly here which one is which, but this is just to give you an idea that these different ways of enabling this communication have a penalty in the data plane performance. And there is a penalty because there is some logical mappings and some things that can happen with the routing of the traffic that makes latency goes up or down. As we see here, the cluster IP and the node port, the latency is not, I mean, for people that look at microseconds, they would say, oh, this is a lot more. We're talking about here 130 to 140 or more than 140 milliseconds. In my case, which I look at milliseconds range, 2 digits, 3 digits, I don't think this is too painful, but you see that there is some difference in the latency here. This is the lines that are like the field lines. And then we have the throughput. The throughput is quite different. So we're talking here about throughput that are around 700 requests per second to something that goes from 750 to 850. And this is also, again, comparing the different cloud distributions. Again, varying the number of requests play a role here. So we started by 50,000, and this is usually the exercise that we do internally at performance engineering. We go from a number that we know from empirically that worked on previous versions or worked on applications that we know. And then we increase this number we extrapolate and try to see if there is any breaking point in the system, and we try to figure out why. There is no really breaking point here, but there is some differences that are quite striking. For example, if I look at the throughput from Microshift, or with cluster IP, for example, when we increase from 100 to 150,000 requests per second, we drop from maybe 15%, 20%. We are talking here about 775 to 750. So this is also something that we started capturing more, if we're dropping these requests or what's happening to these requests, if they are very, very high delayed compared to the ones that arrive. So there are some implications and some issues that we found here when doing our exercise about our setup, where the nodes are placed and the communication overhead between them. For example, if you want to deploy a larger cluster, you probably, for example, in my case, I usually work with bare metal machines. So if I talk about a cluster that has 10 nodes, in my case, it means 10 machines. And then the communication between these applications, they go via the physical network. It's not only within the cluster or some virtualized environment like we have the microstack, but they go over the physical network. So we start having, so you have to consider that the physical network also plays a role here. So we had some limitations in the control environment, as I mentioned before, because we didn't have a larger test bed to evaluate, and not we had some limitations with Microstack as well. The traffic for the IoT applications that we are using. So as a platform company, as Red Hat is, one of the challenges that we have is to understand what does the application need from me, needs from the platform. We don't want to build a platform that is tuned or specific to a certain application. We can do that. We could create different profiles that apply configurations to the platform, and then it's better tuned for IoT or video streaming. But it's very hard to figure out the behavior of the application. So we usually don't, as we don't know the application, we don't own this piece of the end-to-end. Sometimes we have to rely on open source tools that generate traffic, and we have to trust that this traffic is realistic. And then we test our systems with these tools. And of course, there are some practical considerations in the COD here. This is basically the acronym that we found for the edge cloud platforms in the paper. So summary from the study, the exercise we did here. The Key-tray-S showed to be the most resource efficient and showed also the best overall performance in terms of control plane, the resource pressure, and the data plane. Micro Kubernetes came as a second candidate here. Some issues with the control plane, as I showed before, these spikes that were quite strange when we started increasing the number of deployments or the number of objects that we created. It is, though, the easiest one to get installed. Microshift had the slightly better data plane performance. I have to be honest here. There was a better data plane performance with Node port, but as we saw in the graphs, they were not very big compared to the other ones. There is an issue with the control plane and worker nodes being on the same machine, so we cannot split the resource consumption very well. And the Key0S had the better data plane performance. It is also somewhat harder to troubleshoot and try to find out issues with the platform when you are running these workloads. So a recommendation that we have here for people going down this path here is try to tailor the for you to select your edge cloud platform, try to find some practical performance considerations if data plane is very critical, or the operations in the control plane could impact your application workload. And then you have to try to tailor this these inefficiencies or the efficiency specific to the application that you are trying to deploy. With that, I would like to thank you for staying here. My email, Muhammad's email, which is my colleague at the university that run the measurements. And this study here was run as part of the Codeco project, which is funded by the European Union. Thank you.
Thank you, Simone. I must say, I was impressed by the students today for this seminar. Let me share. If you can stop sharing, I will quickly share with you a few of the good questions that they have put together as part of their.
There is one here in the chat.
Okay, you can take that.
Maybe I can read this here from Eduardo. As a layman in orchestrations, can I understand that microservices are the way to facilitate an orchestration? At least one alternative to achieve an orchestration. Yeah, I mean, this is how you. I mean, as we saw in this monolithic architecture or this VM-based architecture, an orchestrator only makes sense if you have the logic of your application broken in multiple pieces as in containers, and you need to manage, create, recreate, do all the, I don't like this word that much, but all the life cycle of this application as they are running, you need someone to take care of that, orchestrator. If you're doing very large scale deployments, you're certainly not writing scripts that deploy 1,000 copies of your application. And if one instance of your application, one replica crashes, who's going to restart that replica? Who's going to make sure that maybe a user that is reaching that worker node is not having any problems because the application crashed? So the orchestrator is this layer puppeting all these management functions for you as a developer, and the only job that you have to do is to write and test your application well, I would say. So it is a term that comes with the Kubernetes and microservices road. I haven't seen this in connection with the other. I mean, you can orchestrate VMs. You have also the needs of the industry sometimes are very strange, but we have OpenShift today, or you even have Kubernetes that orchestrate VMs because they didn't want to do the exercise of, or maybe they cannot, to rewrite applications as microservices. So they just have thousands of VMs to be orchestrated. This is the way of public clouds, for example. They provision VMs for users to use in their environments, and several other industries do that. So orchestration also in the case of VMs, I would say.
Good. I was going through the questions here and trying to identify good ones. And as I said, there are a couple of good ones. Let me try to summarize in essence what I can see from their questions. And I think most of them, they want to know beyond performance. So beyond what you have presented, what are critical technical reasons to choose one or the other? Or here, beyond your use case factors or industrial IoT requirements was another.
This is a good question, because for me as a user, I would look at the resource requirements, right? I have hardware where I want to deploy one of these platforms, Kubernetes or Microshift, but this tells me nothing about the performance, right? It just tells me how much CPU and how much memory I need. So this is a little bit of like a two-layer evaluation here. Maybe your sysadmin is going to choose the one that needs less CPU and less memory, but at the end of the day, is this the platform that's going to deliver the best, as we said, the best data plane performance for your application? Maybe not. So there is this is like this is a good question, because maybe you go for the least resources, but then the performance.
Right. Then here, this student is mentioning about the heterogeneity at the edge that we can foresee, mixing ARM-based GPUs, or maybe some AI type of accelerators coming also at some point soon, more mainstream, while keeping lightweight and secure. This is how this platform should be evolving. How do you see? Do you see them capable? Do you see them on the roadmap of this heterogeneity, or maybe at some point you say, okay, if you need
for the hardware, if you need some of these edge platforms with some specific hardware because your application needs something very specific, this is the job of the orchestrator, or even the scheduler, to figure out. As I said, the scheduler has very basic functionality. It usually looks at, oh, does this machine has enough CPU and enough memory to host my application? And then it deploys the container there, the pod. But you could consider many other metrics. You could consider hardware alignment. You could consider some special hardware that the application needs to run the workload. I mean, that you need some specific hardware, you can probably specify that in the YAML file. You can also say, the YAML file is a place that you can specify a lot in terms of behavior of the application and resources that the application need. For example, if you want to do data acceleration in Kubernetes, DPDK, or basically skip the kernel networking and go directly into the NIC, you can specify these sort of things in the YAML file. You can say which CPU core you want your application to run, which one is isolated, which one is not, how many huge pages you need. You can specify that, and your application is just one line there. This is like the image of your application, but there is a lot of other configuration parameters that you can put in this YAML file. There are lots of memes about that as well, because you can do a lot of things wrong in the YAML files, and you never know what your clusters are actually running.
Yeah, I think that's a good message. And every time I see this IoT, I think about this T. What is the thing? Because not everything is the same, right? A sensor and an actuator, and that. But that one, we will need to leave it for the next time, because we are out of time. It's 2 p.m. Brazil time. Students are starting right now their afternoon classes or other commitments. And thank you, Simone. Great having you here, and looking forward.
Thank you very much.
Keep safe. Hello, and see you next week. Next week, another seminar. Okay?
Yes.
Stay tuned. Thank you.
Thank you. Thank you very much for staying, everyone. Bye-bye.
Bye, everyone. Thank you so much.
Thank you. Bye-bye, guys.